Good afternoon, everyone. Today we're going to look at a basketball following a projectile motion, and we have the height of a basketball being modeled by this parabolic function. Okay, so if we want to draw a quick sketch of what this will look like, just so that we have a visual model of what we're working with. If we have our independent variable t for time and our dependent variable height as a function of time, graph like so, we know we have a h-intercept at 8, right? That's the initial height. Now, when we shoot a basketball, obviously it goes up and then goes down, so it's going to look something like this, right? A very rough sketch, just have an idea of what we're going to be working with. And so, h of t is negative 5t squared plus 12t plus 8. Now, part A asks us to find when it hits the floor. When it hits the floor, we're going to be over at this point here, right? That's precisely when the height above the floor, right? The height above the ground is equal to 0, right? This is when h is 0. So for part A, we're going to set h equal to 0. And since h is equal to this, that means that we're solving the equation. 0 is equal to negative 5t squared plus 12t plus 8. Okay? So we're looking for the roots, or the, in this case, t-intercepts of this function, and so we set h equals 0. We're solving this equation. It doesn't look like we can factor this even with decomposition. I don't believe so. Two numbers that add to make 12 multiply to make negative 40. I don't believe we can find those. So let's use the quadratic formula. We can have x be negative b, so negative 12 plus or minus the square root of 12 squared minus 4 times negative 5 times positive 8 all over 2 times negative 5. And that means that we have negative 12 plus or minus the square root of, that's 144. Negative times negative means a positive. 4 times 5 is 20. 20 times 8 is 160. So plus 160 all over negative 10, right? And we're just chugging along. That is negative 12 plus or minus the square root of, that is 304 all over negative 10. 304 that's divisible by 4, because that's 76 times 4, and then 76 is 4 times 19, so this is actually 16 times 19, and so I'll just make a note of that. The square root of 304 is equal to the square root of 16 times the square root of 19, which is 4 root 19. So if we really wanted to, we could go down to negative 12 plus or minus 4 root 19 all over negative 10. And then we could even simplify that. X would be negative 12 over negative 10. That's positive 6 over 5. So that is, we can write that as 6 over 5 plus or minus 4 over 10 is going to be 2 over 5, so 2 root 19 over 5, like so. And now we want to know which one of these roots, sorry, I'm using t and x interchangeably here. Maybe that's a little bit lazy. Maybe we should be more careful with that. Let's change our x's to t's to fit the context of the problem. There we are. And now, this is going to be 1.2 plus or minus 2 root 19 is some decimal value. So we can go ahead and find that. You'll need your calculator. So we'll have 2 times the square root of 19, and we divide that by 5, which is 1.74. Okay. Now, 1.2 plus or minus 1.74 will provide us with our two t-intercepts in this case, but if you think about what those are going to end up looking like, if we subtract 1.74 from 1.2, we're going to end up with this nonsense t-intercept that would be back in time, right before we ever launched the basketball. And so we know that one is not the one we want, right? This is nonsense within this context, right? And so the one we want is going to be at t is equal to 1.2 plus 1.74, which is where t is 2.94. That's the t-intercept that we're looking for. And so here we have the point 2.94, comma 0, and that is the answer to part A, right? At t is equal to 2.94 seconds, right? Now, part B asks us to find where it reaches its maximum height. And so if we're looking along the parabolic path of the basketball, its maximum height is going to be up here at what we know as the vertex of our parabola, right? And so the vertex is always in between the two roots. Now would be a nice time to perhaps get the negative root, even though we're not using it as an actual solution to when it hits the floor, it can still be useful in finding the vertex because we know the vertex is always in between the two roots. Conversely, you've probably seen by now that the maximum height is found at the vertex, and the vertex has an x-coordinate. I'll make room for it here. The vertex has an x-coordinate that is negative b over 2a, right? That's another approach to finding it. And so let's go ahead and use that formula for now. Negative b is going to be negative 12 over 2 times negative 5, which is, sorry, again, I'm using x. Please be mindful of your variables. We're using t here. So let's use a t. T is equal to negative 12 divided by negative 10, and so t is equal to 1.2, right? That's going to be the t coordinate of our vertex at 1.2, right? That's this number here, not coincidental. And to get the h coordinate of our vertex, we can simply plug in that t value of 1.2 into our original function and find the corresponding height. And so we want to know the height at 1.2 seconds. We're going to plug in 1.2 in for t in our function, and we'll have negative 5 times 1.2 squared plus 12 times 1.2 plus 8, like so. So that's negative 5 times 1.44 plus 12 times 1.2 is 14.4 plus 8. And that means we'll have negative 7.2 plus, that's 22.4. And that means we have a maximum height of 15.2 meters. So 1.2 seconds after being released, we have a vertex at 1.2 seconds later, 15.2. This would be meters above the ground. Okay. And there we go. So we'll find its maximum height. H is equal to 15.2 meters. Okay. Presumably, I probably should have used units of feet instead of meters, because this would mean that somebody is shooting at that is 8 meters tall, which might be a bit of a stretch. But for the purpose of this example, we'll kind of roll with it. And finally, part C is maybe the trickier part of it. We want to know for how long was the ball above 7 meters, okay? Now, it's being launched from 8 meters. 7 meters is going to be, 7 is going to be roughly around here on our graph. And so it's above that 7 meter threshold from the start up until it hits a height of 7 meters on its way down, right? Up until it reaches this point on its journey. And so we know the height at that point, right? The height at that point is exactly 7. That's what we're solving for. And so we know the h coordinate over here is 7. What we don't know is how much time has passed by that point. And so if we know the h coordinate and we want to find the corresponding t coordinate, we can simply plug in 7 in for the height. And then we can solve for the corresponding time. The same way we did at the very start with the height of 0. Now it's a value that's not 0, but it works all the same. And so let's try that out. So for C, our height is equal to 7. So we're going to plug in 7 in for the height. And we'll have 7 is equal to negative 5t squared plus 12t plus 8. Okay. Now, to use our quadratic formula, we always want our quadratic equation being equal to 0. So we subtract 7 from both sides, and then 0, as we wanted, is equal to negative 5t squared plus 12t plus 8 minus 7 means plus 1. And now, again, we can plug this into the quadratic formula. If you go ahead and do that, you'll find your, you'll find 2t values. We are running out of space here. Let's do it over here. T is equal to negative 12 plus or minus the square root of 12 squared minus 4 times negative 5 times 1 all over 2 times negative 5. So t is, again, just plugging our a, b, and c values into our trusted quadratic formula. So that is negative 12 plus or minus the square root of, that's 144 plus 20 all over negative 10. So t is equal to negative 12 plus or minus the square root of 164 all over negative 10. 164 is 4 times 41. And so we can write this as plus or minus 2 root 41 all over negative 10. And so we can write this as negative 12 divided by negative 10, we know is 1.2, plus or minus 2 over 10 is 1 over 5, so the square root of 41 over 5. You might wonder where that negative is going, but since we're taking the positive and the negative is being absorbed either way. And so we can simply write it like this. And so that means that we have t is equal to, again, if we subtract this value from 1.2, right, we're going to get a negative value, right? Because in theory, we would hit that 7 meter threshold somewhere back here. But that would be back in time before we ever shot the basketball. That's not the point we're interested in, right? We're interested in this point at t is equal to 1.2 plus the square root of 41 over 5. And so let's plug that into our calculator and find that exact, or approximately that value. So that is the square root of 41 divided by 5 plus 1.2 plus 1.2. And so we find that t is approximately 2.48. Again, we should use the approximate symbol since we are rounding. And so that's the value we're interested in at t is equal to 2.48 seconds. The ball falls down to a height of 7 meters. And so from the time it was released through its vertex down to where it finally reaches a height of 7 meters, it was above 7 meters. And so we can write a solution for approximately 2.48 seconds. And that's everything. So we found when it hits the floor, meaning the t-intercepts, the roots, right? We found its maximum height. We know the time that we reach the vertex is always between the two t-intercepts, or if you rather, we can use our trusted negative u over 2a formula, right? Once we find the time where the vertex is located at, we plug it into our height function to actually find that maximum height, which we found to be, where is it? 15.2 meters. And then if you want to know how long it was above 7 meters, we're going to plug in 7 in for the height. That's over here. We want to make it equal to 0, and so we subtracted 7 on both sides. Now we're again solving an equation where it's a quadratic equal to 0, and so anytime we're in that scenario, we can use our quadratic formula. We're going to have irrational values, and so we're going to round to 2 decimal places. That's why we use the approximate symbol here. It's an approximation cut off at 2 decimal places of 2.48 seconds. That's this point here, and now understanding the context, that's why I always encourage my students to draw a rough sketch. You don't have to spend much time drawing the graph, but just so that you understand what's going on and what we're actually going to be looking for, right? Understanding the time that the ball is above 7 meters is going to be from the release point, because it's already above 7 meters there, through the vertex, down until it falls below 7 meters. And that entire time interval is the time that the ball was above 7 meters, okay? So I hope you're getting more confident working with quadratics. I hope this is starting to connect some concepts together, and thank you for watching.